So you can actually arrange the cycles as per how you want it. So this is what it looks like, the Verilog code, what it looks like. It looks like a state machine actually. You can see this block here now. Let me just explain with one block. So just the way I explain with one block, that's where the rest are. So it says when case is taking case state is a Verilog code case state. So it's more like a state machine, but in actual sense that's the instruction cycle of the CPU. So it says when is in reset state. Now this is what I have here on my code here. I have it when is in reset state here. Let me circle it. Then the AC control is in reset AC, reset CC, reset IS, reset SP, reset PC, reset OP. Everything is in reset. Now let's go to the here. You can see it. Everything is in reset. Everything reset. Everything is in reset. And the next state is reset 1. So and that is what you have here. That the next state is reset 1. So that is what I did for every single thing you can see here. So each of the states I extracted the data and placed them in Excel. I did it one after the other. This GSL state here now. You go here, you can find the, let me find it. Jump to subroutine. You can see it here. GSL state here. All these values in it. These are the values. These are the values here. With this next state. So then again, the ones with asterisk OP. So the ones with asterisk OP, something like this one here with asterisk OP, are the ones whose values are dependent on the opcode. Now let me show you what I mean by being dependent on the opcode. So let me see what state is in. Let's find the fetch state for AC, CC and IS from the Verilog code. Fetch state. Now this the first state here. Now instead of giving those values, it now said case for OP when between 7 down to 4. Now the value are no longer values in the first state. It is now giving you values whenever is in first state. The values are dependent on the opcode. So that is why I have my second Excel sheet. That is why I have this sheet. So this sheet here takes each of those particular states that are dependent on the OP. It treats them separately. Instead of having one line as the first state, it now has it extendedly with different values of the OP is 8 bits. So it takes from 000 to until is 11111. Takes it until is, you can see until is, you can see the last one here. So it's total of 258 values here until OP is 111 and gives different values for it. So the idea is just to help you understand the code. So now it says when it's in first state, now it says case OP 7 down to 4. 7 down to 4. When it says 7 down to 4, it means the first 4 bits of the opcode. Now it says when it's 010. So what it means by these values here? These values means when is in first state and the first 4 MSB bit is 010. These are the values you take. Let me show you. 0100 and is in first state 01. Now this is where he's talking about. This is 7. This makes it 8. There's a 0 here to make it 8. So it says when these first bits are 01000, so you are no longer considering the LSB, the remaining 4. It's just taking in consideration only the first 4. So you are going to take something like from here up until here. So that particular place is referring to this space here. This particular 010 here. So there the AC control is load AC, CC is load CC, latch IS, latch SP, and AC left. So when we go there, so you now see that the AC there, the whole AC is load AC, load CC, latch IS, and AC left. So everything there for AC, CC, IS, and left control, we have that particular value. Then it said again, let me do it properly. Then it says again, then after this first 4, is now considering the last 3 down to 0. So it now says when 3 down to 0 is 000, then it gives 2 value for 0 right and LU negative. So you now go here again. Where is it? It says when the last one is 00, that is only referring to this particular line where the last 4 are 000. So it's only talking about here. It says 0 right and LU neg. And I go back there again. It says when it's 0011, it takes these 2 values, 0 right and LU con. Then I go back there. I set it to 0 right and LU nope. Okay, sorry, it's LU com there. Let me check. Okay, yes, because it says one is in 0011, which is this one here, is 0 right and LU com. So that is how I went through this code, picking up all these values and fixing it in the Excel sheet. So in a case where it doesn't give cases for OP, something like the reset state which we talked about, and some state down here, some state like this one, something like JSR was just plain listed, BSL was plain listed, that means you won't have any need for this Excel sheet too. You just go to the main Excel sheet and fixing those values. So after fixing in the values, for you to put them in actual ROM, you have to convert them to binary or hexadecimal bits. I know in real world you have to convert them to binary, but in Logisim I converted it to hexadecimal bit before I filled in the ROM. You can use an EPROM programmer with Python code and the software programmer to do it. You take the code, those values, and fix it there. So I was explaining it earlier how I did it with this my Python code. So actually I used maybe 4 to 5 Python codes. I used the split, the binary to hexadecimal, because Logisim was taking only hexadecimal data, so I converted binary to hexadecimal. That's why I have this particular, I wrote this script in Python, binary to hexadecimal. Then you have this clear. What was clear? Okay, clear I was using because the Python code went through. I didn't actually start separating the one after the other. It looked through the script. So it was removing things like these stuffs, removing things, the comments, we were removing the comments out, and then extracting these values one after the other. It was extracting all these values. So that was basically what this clear script was doing. It was removing all these stuffs from me, removing them. These are the comments that I encountered. Then the web.py, they replace. Okay, I use the replace to remove spare zeros, because I told you, take for instance, if the control bit was using only 2 bits, I added extra bits to all of them. Take for instance, if the EA is just a 2-bit, that means I made it to be 3. So what the third bit does was to store a particular value for me. What that value does is, if it's 0, it means it's normal, take only the first 2 bits. But if the third bit, the least LSB, which is the third bit, is equal to 1, it means that the data has an effect from the opcode. That means refer to the second Excel sheet. So in the circuit here, that is what happened here. All the ones that have only one ROM means that they didn't have anything to do with the second Excel sheet. So it was just only one Excel sheet I used for them. Something like this OP control. This is the Excel sheet here. When you go through the OP control, this is it here. You find out that there was no asterisk OP in it. So it was just all values in it. It was all values in it. But something like the AC control, so I added an extra bit to it, the LSB. So it now takes it and compares it to 1. If it's 1, refer to this second ROM. This ROM is the second Excel sheet that had to do with the OP control. So it shows that the data actually had something to do with the OP. That is, the OP is affecting it, which is, these ones are okay, not something like this. But when you go through the script, you see something like case OP 7 down to 4, case OP when 100. You can see them here, when 100, when 101, when 111. I took them and placed them in the second Excel sheet. So that's why some of the ROM are single, some are double. The extra ROM were for the second Excel sheet, and this comparator checked if the last bit is 1. That means you have to use the second Excel sheet. If it's 0, use only the first Excel sheet where I store the data. So this is how it works also in real life. Check them. So that was what I used this rep to do. There were some I removed 0 and some I added 0 to them. So if you need any of this sheet, I can actually give them to you. So this is a very important script. This particular Python script does the conversion from letter to binary, from binary to letter. So this is where I swapped. I used the binary dictionary. So what I did was, I took each column of this cell, then I used this Python script to convert each of them. Assuming you have /md, it is going to replace the /md with 110. If it comes in contact with say it sees increment PC, it checks the dictionary and checks for what increment PC means. So increment PC is 0010, so it replaces it with 0010. So that was how I was able to transfer this particular sheet to this third sheet here. So they're all the same. This is the binary version of the lettered one. So from here, I now took each of the column again, converted them to hexadecimal before I took it to logic. So, and that is how these ROMs came about. how they came about. Remember, I told you the states are the controller. The state is what controls those ROM. You can see that's the signal where the whole ROM are taking the address. The ROM here, this is the address. It takes the address and gives an output. So there was one exception where I wrote as a IRQ. It wasn't much, so I didn't make an extra ROM for it, or maybe an extra Excel sheet. So I used the kind of map to draw a separate table for it. So this was why I added this extra circuitry, but it's still very easy. If you go through the code, you see where the IRQ actually came to affect, and see. So all this, the code state, this one's an OK. You can see where they say case OP 7 down to 4. So for me, whenever I meet something like case OP 7 down to 4, 7 down to 0, I took them to the second Excel sheet, so that the first one would be neat. So that is everything that has to do with the CPU. I've talked about the flag, I've talked about the ALU, and now I've treated the state machine. So this is what the ALU looks like. But at the end of the day, not everything was needed. We only needed, remember, this is the ALU, the CPU address that goes into all this address we've been talking about in all the peripherals we treated earlier. This is the data out, that is the CPU data in that goes into all the peripherals. This is the read write and the VMA valid memory address. It needs to be on for the CPU to read or write. And the read write means if it's on is reading, if it's off is writing. So this is the data, CPU data, the address is reading or writing from, and this is the data that is being sent from each of the peripherals. These are their interrupts also. I think I've done very good justice to the CPU. That will be all. In the next tutorial, I'll be rounding up summary of the whole circuit. Thank you, and subscribe to my channel, please.